Okay, physical science time today. Today you're going to take notes. Today we're going to discuss your favorite topic, which you love to do. You even have a sheet of this that's due on Tuesday. Work! Work and power in simple machines. Today's topic is work, power, and simple machines. Do you get my joke about it's your favorite thing, work, because you guys all behave as if you're unemployed? Would you shut that door, please? Meaning that when I give you something to work on, you either don't or you complain about it. Today's topic is work, power, and simple machines. The objective is to diagram energy changes. Where is it? Diagram energy changes in simple machines. So the simple machines is kind of the, culmination or the tying together of the lesson. But first we're going to talk about work. Actually, we're first going to talk about energy, which we talked about last time too, but work and power, and then relate those to simple machines. Diagram energy changes. Diagram energy changes in simple machines. Remind me, what is energy? Yeah, almost the ability to cause change. So remind yourself that energy, this is probably the most important concept, not only in science, but in the world. Energy is the ability to cause change. And we talked last time about how we can measure that depending on an object's either position, which is its potential energy, or its motion, which is its kinetic energy. How much change it has the ability to cause because of those. And now we're going to talk a little bit about work. I want you to remember that, what was the unit we used for energy? Joule. And that was a kilogram meters squared per second squared, which was a joule. This whole pile of base units, kilogram meters squared per second squared, is equal to a joule. One of the ways that we discuss energy, one of the ways that we discuss the ability to cause change, is by talking about how much work it takes to do something. So work has, among freshman boys, work has a negative connotation because it's something that you necessarily don't want to do, right? Joe was just explaining to us about his weekend, how he's going to work all weekend instead of play Farmville or Harvest Moon or Farming Simulator 22. He's going to have to farm in real life. So that's something that people do. That's kind of the American way, is to complain about work, because work is something that requires energy. Work is something that requires the ability to cause change. And in science, we have a specific way of defining work, which is not just whether something is difficult or not. But in science, we use this formula. Work equals force times distance. Work equals force over a distance. And by over, I don't mean the mathematical operation division. I mean that when force is applied across a distance, we use this equation. This should be a little x because it's something that in math is called the cross product, because we only use the component of motion in the same direction as it, or the component of force in the same direction as distance. So we want it to be like this, where W is, can you guess what W probably stands for? Work. Weightlifting. Yeah. We'll talk about that in a second. That's a great example. F is force measured in newtons. And lowercase d is distance measured in meter. Remember, again, that a newton is a kilogram meter per second squared. Do you remember that? A newton is equal to a kilogram meter per second squared. So in a way, this is the third way we have to arrive upon the measure of energy. Remember, we had kinetic energy, 1/2 equals mv, or sorry, K equals 1/2 mv squared. We had potential energy, U equals mgh, and both of those ended up equal to joule, right? 1/2 mv squared and mgh both ended up equal to a joule, a kilogram meter squared per second squared. Now check this out. If we take a kilogram times a meter divided by a second squared and multiply that whole thing by a meter, as it tells us to, what do we end up with? Kilogram meter per second squared multiplied by a meter, what? Simplify this expression. We just multiply kilogram meter squared per second squared. Do you recognize this little guy? This is the same as that, which means it's the same as a joule. So again, we measure work in joules. Sometimes we measure work in Newton meters, but that's an uncommon way to do it. Usually that unit Newton meter is reserved for torque, but this is how we measure work. And it's really important that we know that these two things, force and distance, must be in the same direction. So your boy talked about weightlifting. I'm going to try to keep my thumb in this page so I know what I'm talking about still. Ooh, this is a weight. What does weight mean in physics? No, not just how much mass, how much gravity is pushing down on it. Yeah, so this has a particular weight, right? If I lift this weight, ooh, like a weightlifter, oh, yeah, I am expending energy to do that. I'm causing a change, aren't I? Am I causing a change? Yeah, I'm changing its position. I'm giving it potential energy. I'm also moving. I'm giving it, or I'm causing it to have kinetic energy. Now, the work equation tells us that force and distance must be in the same direction. What force am I putting on this when I lift it like that? I am pushing it up. So what direction is it moving? Which direction is the force moving? Up. Yep, force up, and the distance it covers is up. So is work done? Yeah, they are in the same direction, so work is done. Now check this one out. What direction am I putting a force? To hold it here. Just to prevent it from falling, which direction am I putting a force? Up. If I walk with it this way, what direction is it moving? So is work being done in this case? No, because in this case, or in that second case, the force was up, but the direction was, or the distance was that way. So work was not done. So you have to be really careful when you do these work problems. Was work actually done? And that only happens if they're in the same direction, okay? And if you were really asking great questions, you might ask, well, what if it's some angle? What if it's only, like, what if Mason is mowing the lawn, mowing the lawn with a hockey stick. He's just doing that Japanese side thing where they just, anyway, he's mowing the lawn, and this could not be a worse picture. Let me at least get the exhaust pipe on there so we can see that it's polluting the atmosphere. He's putting a force down and to our left, right? But it's moving, yeah, it's moving just left. So what if the force and the distance aren't in the same direction, but it's kind of in the same direction? The answer is, when you get into physics, you'll see that forces are made of components, and so we only use this, what we call the x component. In this case, if the direction is in the x, we'd only use the x component of that force, which is a smaller part of it. And that's why this little x is here, which means that we would do trigonometry. Basically, we use the cosine of the angle subtended by the force compared to the distance. But you don't need to worry about that right now. Just know that if they're in the same direction, we multiply them. And if they're perpendicular or in opposite directions, we don't do the math. There was no work done. In someone's lab, did you do work in your lab where you climbed up the stairs? Yeah. What direction did you move? Up. Well, you moved up and south. I mean north. Up and north. But the force was also up too. So you did do work. Now, what was the difference between your first test where you walked up the stairs and your second test? Or skipped. I don't know. Skippity toilet. I don't know. What was the difference? Did you apply more force? Well, how do you know how much force you applied? It was just like in the case of the book, the force you applied was the same as your weight. But yeah, the force you applied was the same as your weight. So did you gain a lot of weight between the two tests? No, so that didn't change. Did your distance change? No. So the work was the same in both cases, but you felt different, right? Why? If you if you run up the stairs, you're doing the same amount of work as if you walk up the stairs, but why does it feel different? You're going faster, exactly right. There's a time component. So the next thing we talk about is power. Power. Power is how fast work is done. Or how fast energy is. I'm going to use the word expended, kind of hearkening back to the energy budget idea. How fast energy is expended. Power is abbreviated with the capital Latin letter P. Power equals either work divided by time or power equals energy divided by time. Either one works. Why would these both work? Think about the units. Why would both work and energy work? Why would both work and energy apply? Yeah, they're both measured in joules. So we end up with, P, capital P is power, W is work, E is energy, and lowercase t is time. What do we measure both work and energy in, as you just said? Joules. What do you measure time in the SI? Seconds. So power is measured in joules per second, which we call a capital W watt, named after James Watt, a Scottish physicist. You've heard of a watt, probably. Where have you heard of watts before? Light bulbs. Light bulbs have a particular, what sometimes in America we call wattage. They have a particular power, and that power is measured in watts. How much energy they let out in a given amount of time. Do you understand that's what makes higher power or higher wattage light bulbs brighter, is that they're expending more energy in an amount of time. These are LEDs, and so they have kind of crazy numbers. But maybe these are 8 watt LEDs. If they were 4 watt, they would seem what to us? Dimmer. Not because they're using less energy necessarily, but they're taking a longer time to expend that same amount of energy. What's the reverse of that? Why would anyone want to use a lower power light bulb? Save energy, yeah, to make it so that the energy lasts longer because we're increasing the amount of time effectively. So power is just how fast work is done. And so whether you haul your human mass up the stairs at a rate of a stair every 20 minutes, like some of you do when you're on your way to class, or if you go up the whole staircase in 13 seconds, you're doing the same amount of work, but the time is different, right? Smaller time means bigger power, bigger energy expenditure per unit time. Do you have questions about that? Do these equations make sense to you generally? Yeah. Okay. So really the last thing we have to talk about is a simple machine. Let's just keep, I'm going to erase the work equations up here. Does anyone still need these? I might also erase them. Oh, you silly idiot. You erased it before the kids were done. Are you not done? You don't have to get it off your friends. Oh, you was just joking. Then you made me feel like a silly idiot, but I'm not really. Let's just keep the picture of Mason's long body and the barbecue grill up there because we're going to use this for simple machines too. There are basically 2 kinds of simple machines. The 2 basic kinds of simple machine are incline plane or inclined plane. Some people say one and some say the other. And lever. You'll remember from your vocabulary, which again, let me remind you that the point of your vocab is so that you can learn the words of science. So you really should have learned from it. But you will remember from your vocab that there are more simple machines than this. But these are the 2 basic kinds. All the other ones are offspring of these, if you will. So What about this diagram could be an inclined plane of Mason mowing the lawn? Where do you, just make up something, in what part of mowing the lawn would an inclined plane ever be used? God bless you, Jim. God bless you again, Jim. Yeah, well, okay, so let's pretend, well, for one thing, what if there's a little hill here, right? That would be an inclined plane, right? It's just, the point of an inclined plane is that maybe, right, there's higher lawn up here and lower lawn down here. God bless you, Joe. And by having this hill here, you're going a large distance or larger distance compared to the height. God bless you, Joe. Would it be possible, if this inclined plane weren't here, could you simply lift the lawnmower up this height? Yeah, but it would take more force, right? Whereas you go this longer distance and it takes less force. Because at its best, even with a simple machine, work can't be increased. So let's say we have the same work in both cases, but maybe if we're just going to lift the lawnmower up, we're using a large force over a small distance, and when we roll it up the inclined plane, we're using a small force over a larger distance. But you see, work is still the same. It's a trade-off. That's what simple machines do. They can't increase the amount of work done. That violates the law of conservation of mass. Simple machines don't no increase in work or energy. You can't get more energy out of a simple machine than you put in. But it could match. And what it does do is it changes the ratio of force to distance. Like you might remember from Joe's pulley example that when he had that system of 6 pulleys on there, he pulled the string about 10 times as far as the little weight went, but it only used a tenth of the force. So he had big distance, small force. And you can see where that might be useful. In this case, it's useful because you don't have to hoist the whole weight of the lawnmower up that far. You move it over a larger distance and a different height. Where's the lever used? How's the lever used on this? Yeah, you have the little squeezy thing. Let me put that on here. That's a lever. I mean, it's kind of a lawnmower is actually an example of a complex machine, a system of simple machines working together. But you have this lever here that when you put force here, it turns a little thing in here. Another thing is that these wheels are levers. So the types of lever, the other things in the lever family are a wheel and a pulley. Because, I mean, it's a tiny little drawing down here, but if you imagine the diameter of this wheel being a straight line, it's kind of like a lever. You put a force here, and the work is done here. And it just keeps spinning and spinning. So a wheel, I guess the way I drew that, he's going backwards. No, he would be going forwards. A wheel and a pulley are both examples of levers. What's another example of an inclined plane? From your vocab. Screw. A screw is an inclined plane that's just wrapped around. I'm really making a mess of this. Wrapped around a rod of some kind. So we have the rod there, kind of like a nail, and then there's a inclined plane wrapped all the way around it, so that when you twist, it moves it down. So you're putting a certain force, kind of like the lawnmower here. It changes the direction of the force. So you're putting a torque, which is a twisting force on it, and instead of just twisting, it also moves down or up, depending on which way you're turning it, because the inclined plane changes the direction of the force. And what's another example of an inclined plane? From your vocab. Wedge. Yeah, and a wedge's job is to change the direction of the force. 2 examples of a wedge. We use a wedge to hold the door open, right? When the door is held open, I guess I'll draw over here now. I should probably draw it in the same box as the inclined plane box. So when the door is held open, here's the door in cross section. Here's the wedge. the wedge is changing the direction. So the door wants to, right, close. The door has a force on it that causes it to go this way. The wedge uses force that is actually pushing down on it to also push sideways on it to resist the force of the door. How is it pushing down? Well, because between gravity and the normal force, it's wedged in between the door and the floor. And so friction holds it there and it changes the direction of the force. Another example of a wedge is, I have one in my pocket. Now I can't post to YouTube. It'll get canceled. But a knife is a wedge. A knife is a wedge because in cross section, this is the knife in cross section. Here's some bologna or a cat or something. But this is in cross section. You push down with the knife and it goes into this, sure, but it also splits it like that, right? It's wedging it. That's a type of inclined plane. So simple machines, their job is to either change the ratio of force and distance or change the direction. That's another thing the pulley does, is if you have even just a single pulley, and here's you hauling on the pulley with your really long arm and your short little body, you can pull down. You are biomechanically more advantageous at pulling down than you are at lifting something up sometimes. And so maybe you want to carry this load. The pulley makes it so that you can pull down and this will go up. It changes the direction of motion. How much it does this, how much it reduces the amount of force is given or is calculated by the equation for mechanical advantage. Mechanical advantage equals force out divided by force in. Mechanical advantage is force out divided by force in. So it's basically telling us how much we can multiply the force by using a simple machine. And the other thing we talk about is efficiency. Efficiency of a simple machine is work out divided by work in. What's the highest this can possibly be? Efficiency. I already told you that a simple machine can't put out more work than is put in. So what's the highest this could possibly be? 1. Yeah, 100%. It can only be up to 1. Why would it ever be lower? Why would it ever put out less work than you put in? No. What truth of the universe makes it so this is actually never 100%? Can energy ever be lost? No, but it does. It's thermalized, yeah. It becomes friction. So even in the case of the knife with the bologna, how I can put in a certain amount of energy and it'll never actually get that much change out of it as I put in because there's a little bit of friction. Same thing with the pulley. There's a little bit of friction up here on the rope. Same thing with the wedge. That's actually, friction is helping the wedge in that case. Some of that energy some of what would have been motion is lost. Same thing with the lawnmower. We never get more out than we put in, and that ratio is governed or is calculated by efficiency. Bye.